So, good evening, participants. Good evening, viewers at home. Welcome to the second day of the deep dive days from the TUM.ai Makeathon, October 2021 edition. I'm your host, Petar Petrov, and today we have another two exciting talks organized for you. First of all, it's going to be a workshop with the topic of Frontiers of AI in Business by Philipp Gerbert. And then we will have a business talk starting at 8:30 p.m. Central European Summer Time on the topic of sustainability and AI by Sebastian Friedrich. However, before we dive into the first workshop, I would like to give out some short information to our participants. That is, I would like to thank all of our sponsors, appliedAI, Unternehmer TUM, and TUM Venture Labs. And I would also like to introduce to you our new sponsor, that is Microsoft. And additional information, if you would like to get special access to Azure for the official Makeathon during the weekend, please comment that in our channels in Slack. So you can use the services of Azure in your project. And other than that, I would also like to mention that the TUM.ai application phase is currently open, so if you would like to become a member, feel free to do so, and we're looking forward to your application. Alrighty, then we can start immediately with our first workshop, the topic of Frontiers of AI in Business by Dr. Philipp Gerbert. He has obtained a master's degree in physics at the LMU University in Munich. He has a doctor of philosophy also in physics from the Massachusetts Institute of Technology, and he's currently the feature shaper at Unternehmer TUM, the director of appliedAI, and he's also the co-general managing director at TUM Venture Labs. Good evening, Dr. Gerbert.
Hey, you can call me Philipp. Yes, good evening there.
Good evening. Are you all ready and set up to go?
Sure.
Perfect. The stage is all yours.
Okay, I'd like to try to share my screen. So can you see this?
We can see it.
Cool. So what I wanted to do today is give you, an introduction of artificial intelligence in business. So AI frontiers and business value. It will also be a introduction to some of the core methodologies for you, those of you not so familiar with AI methodologies, but it should hopefully be interesting for everyone to see how to apply that in the business context, right? So let me skip over the introduction of the TUM and appliedAI. I hope you know it, otherwise you'll get an introduction to both Unternehmer TUM and appliedAI on Friday. Perhaps just two words. So Unternehmer TUM here is the largest entrepreneurship center in Europe. Our startups, we create about a bit more than one startup per week, and it was TUM Unternehmer TUM, and they collect, over $1 billion of venture capital per year. This year we actually had 2.5 billion. And appliedAI is focused really on increasing or leveraging the power of AI for innovation in Europe. So we are on the innovation side. We work primarily with corporate clients in order to professionalize the use of AI. So that's I'm here right now today more as from the appliedAI side rather than from the Unternehmer TUM side. Just for information, I was previously partner of the Boston Consulting Group, and there I led the global AI and business group for 7 years. Exactly, and lots of the things obviously are based on my experience there. Okay, let's go. So I would like to start to really say, before I even define AI or go into any of the algorithms, to say, what are actually the critical things that you need to know if you ever want to apply AI, in particular in a business context? What are some of the typical, so to say, myths and realities? I will show them all, but I won't go through all of them. But of the most important things to say, why is it so transformative and what's so critical about it? So there are a few, myths about AI, conceptualism, that's all in the algorithm, machines, things like humans. I won't get into that. I will focus on, what are the key realities of what you should know about AI and why is it critical in business. So first of all, AI realities. AI is inductive learning. I hope it was inductive, so it learns from examples. One of the obvious corollaries is algorithms are rather short. You will never, I hope ever, write 20 million lines of code in AI as you do for, let's say, Windows, because you essentially give the computer only the learning algorithm, and the program is then written by applying that and in some way to data. Second might sound trivial, but it's actually quite critical. AI works at superhuman speed and scale. What do I mean by that? So electronic signals are about 5 million times faster than your brain signals. Your brain signals are about 60 to 100 meters per second. Typical electronic signals are at the speed of light. Obviously, you can also reach an unprecedented scale and connect systems across the world. That's why, if Facebook makes an AI mistake, it has huge repercussions all over the world almost instantly. These two things are actually not totally compatible, in the sense that if you can act very fast, and that's the typical application is financial markets, then actually you do have a scale problem. For instance, if AI would run financial markets, you could no longer synchronize them across the world simply because of the speed of light. Speed of light takes about 1/10 of a second to go to Australia. That's why if you have a phone call, you think it's kind of synchronized. But if you think that you act at machine speed and do trades at machine speed, then synchronizing London and New York feels a little bit like sending Greta Thunberg with a sail ship to New York and telling them, you just did a trade in London. That's quite known from high frequency trading, where that problem of not being able to synchronize financial markets has been known. But if you actually act with AI, becomes critical. So lots of what you do with AI and why it's so sensitive, in particular, lots of security, safety, ethics challenges depend on the speed and scale. The big breakthroughs in 2012 and then again in 2018 was we cracked vision and language. Vision and language were the oldest standing problems in artificial intelligence ever since the 60s when we created it. And it's quite important because vision enables us to act in the real world, because vision is one of the most powerful ways to orient yourself in the real world. And language enables you to access human knowledge and interact with humans. And so this is one of the most important breakthroughs and obviously totally critical for most of the applications. The fourth one is mainly for engineers. Going non-linear is trivial. As an engineer, you spend your time doing, linear solving things explicitly linearly and then doing all kinds of error correction around that. It was a big surprise in AI how trivial the step from linear to non-linear is, and it's still. I think the first 100 million of business I did with AI was simply based on this sentence, where all the wonderful problems that people solved in a linear way and were non-linear were suddenly accessible, and you could have dramatic consequences. One of the better knowns is actually DeepMind optimizing Google data centers, where they dramatically decrease the energy use. The reason they could do that is because the traditional algorithm for doing that was essentially based on linear algorithm, and it was a non-linear problem, and it was quite dramatic. And this was Google, right? Google running its centers, so it's not a company that didn't know how to run data centers. The other thing is it's very simple in AI to run successful pilots, and they are huge scaling challenges. I'll get back to you. This is perhaps the most important obstacle for applying AI in business. And I'll get to the scale. Because of that, I'll get back to the scaling challenge in a second. You always want to learn from the maximum of data. So you always combine central learning with decentral action. That you can decouple action from learning is quite special to artificial intelligence. That's difficult for human bodies. Take the trivial example of autonomous cars. That's perhaps very tangible. An autonomous car acts autonomously. Obviously, it drives around, but it doesn't learn. It sends whatever it learned data somewhere centrally. It's collected. Then the basic algorithm is updated, it's tested, and then downloaded. Tesla, I think, downloads it every 2 weeks, roughly. The reason is we really want to use the optimal amount of data and make sure it's secure, and then you can download it. I often say submarines don't swim. Machines don't think like humans. They act differently. So please don't try to copy humans. That's one of the most basic mistakes. And obviously, because of the word artificial intelligence, quite common. It's the same for planes, right? You don't want to copy birds. Planes just fly differently. I don't need much of the others. I think AI is no common sense. I'll come back to that. It's obviously only applies intelligence to the domain it was trained at. So, I mean, a chess program doesn't run out of the room because there's a fire, right? To take a very tangible example. We are actually exploring the regions, but even AI models trained on the entire internet still suffer from the problem. That's obviously why you have lots of safety and security issues, because you can have rather trivial problems that it doesn't recognize. We're approaching that, but you also don't want to train it on the entire world because you want to control it. So it's not something that's easy to overcome. I won't go into lots of the others, perhaps just often it's asked, well, you need lots of data and where do you get them from? So it's true, AI needs data, but it doesn't necessarily need external data. The first thing to know is in business problems, the more data you have, the less domain know-how you require, and vice versa is also true. The less data you have, the more domain know-how you require. So when people ask, how much do you have to know? Well, I've optimized copper plants, copper smelters, and I know strictly nothing about copper smelters, simply because I had a used data set and was rather easy to optimize them. And it can get in the way. If you have lots and lots of data, your original domain know-how can be in the way. There's a famous quote from one of the pioneers in language models. Every time I fired a linguist, my language model made a jump in performance. Language is actually quite interesting because indeed over the last 2 years we threw everything we knew of language, or linguists knew of language, just overboard and start rethinking what language really is and how it works. So there's lots to say about data. You don't need external data. Obviously, the biggest surprise in chess was the first chess program that received no external data whatsoever, AlphaZero, that was trained purely by playing against itself, played the best chess ever, and played the most human-like chess, much more human-like chess than all the programs that were trained on humans, interestingly. So there is some kind of basic truth in how humans play chess. So we could discuss hours about data, but it's just something to keep in mind. And I think this domain knowledge and data is perhaps the most useful. Obviously, there are huge security and safety challenges, in particular if you take action. If you don't just provide information, that's true for robots, that's true for cars, obviously, that's true in an extreme case for weapons, et cetera, et cetera. So this is a long list, but I mean, if you internalize that, I think you understand why it is quite powerful. Some of the things are quite powerful in business, and also why it is quite different from anything we've done before. That's why it triggers this huge transformation in the business domain. So that's all very nice. The most common problem you have in business that you think, oh, you have this wonderful plan how to apply AI, but you never reach a return. That's what's covered here. That a miracle occurs. You might need a bit more detail here. Classic, say AI comics, and the reason, and that I just want to point it out. I won't spend a lot of time here, but it's important for you to know it. Is what you call the AI paradox. And we as appliedAI, we work a lot on AI maturity of companies. And we have several maturity levels, not started an experimenter who has his first experiments, practitioner, professional, shaper. And lots of companies are in the experiment level. And the difficulty is what we call the AI paradox. It's incredibly easy to launch AI pilots and achieve very strong results. And it's fiendishly hard to scale AI. Why is that the case? At the very core, it's because you can't separate the algorithm, the software, from the data. About 20 years ago, Regis McKenna and I once had a chat with Hasso Plattner in Silicon Valley, and he told us a story how he founded SAP. And he said, the most important thing to ever have enterprise software take off is that you separate the data from the software. That was not done in the previously customized software. They often had it very interchanged. So you have to separate completely. So databases are totally separated from enterprise software. And if you do that, you can modularize the software and scale it. Now, I think it's a rather nice explanation of the difficulty of AI, because obviously in AI, data write code. So the whole program depends on the data, and you cannot strictly separate the two. And that is at the very core. And then you can write thousands of papers on that, on technical debt and what you name it. Why is it so hard to scale? So if you have a POC as a company, that's not worth so much. And you might, be working on POCs, that's all kind. You have to first do a proof of concept. But I know lots of companies that have 200 POCs and nothing at scale because they didn't build the entire infrastructure. We won't cover it here, but just be aware that in order to build a pipeline to manage AI over the life cycle, to have interacting AI cycles, it's a huge job. Even if you go a little bit further and have some systematic implementation, you still don't see a lot of value. You really have to get a rather systematic production system. So at the top, I depicted the values. So the trouble is all the companies, 95% of the companies are on the left-hand side, where essentially you see no value, and then the value explodes when you really do an AI at scale or even, reshape the industry. That's the big challenge in enterprise, in business applications of AI. So just be aware of that fact. And if people are somewhat a little bit hesitant or say we've tried A, B, or C, that's typically the biggest business problem in AI. Apologies. Okay, enough about myth and reality. Just to give you a little bit of sense, on the one hand, why artificial intelligence is such a powerful thing in business, and also what are the core difficulties you see there. Let's now be a bit systematic and go, okay, what are then the approaches and where are they typically applied? And I start, with very classical machine learning. I go to deep supervised reinforcement and then into attention and foundation models, which are kind of the current state of the art and which change again the way you approach artificial intelligence in business. So let's go. First of all, I do owe you a definition. So here's my definition. Artificial intelligence, machine-based system that perceives its environment, pursues goals, adapts to feedback, change, and provides information, takes action. It's loosely adapted from Russell Norvig, taking an agent-based approach. I think the most important thing is humans do not appear in this definition. Any definition that compares it with humans is not particularly useful. It also doesn't tell you about the degree of intelligence. And it's a little bit for me like speed. a snail has speed and is very different from an animal. It might not have the highest speed depending on what you compare it to, but it's not a plant, right? So it doesn't grow roots. It's just very different from anything. It tries to get away from some of the stuff if it has stress, etc., etc. So that's why, the basic definition of artificial intelligence, please separate it from how intelligent things are, and it's obviously quite difficult in some of the conversations you have. Now, within that, the biggest field right now is machine learning, and actually everything I talk today is only about machine learning. So I use it, frankly, as a synonym, which is obviously untrue, but machine learning is a subfield of artificial intelligence. Lots of the things here I'm not interested at all here, but one thing I should point out, I'm not interested in what people sometimes call GO-FI, good old-fashioned AI, which is rules-based systems. So the first attempt, or a big attempt in the 80s was to do machine learning via rules. And if you ever try to learn language via rules, you get the exception, the exception of the exception, the exception of the exception of the exception, and you drown in complexity. And that was basically what happened. So I think it's except for very, very simple applications, that's a totally abandoned path. So I'm only interested in learning systems. Now, within that, there are lots of methods and algorithms, and I showed just a few, and all of the ones you see here and many more, all are actually quite important in business problems, which might be strange, because if you talk about research, you only read about neural networks, essentially. And I'll get to that. I'll get to why neural networks, also rebranded as deep learning, are so important. Where you use the other algorithms, but just be aware. So I will dive into deep learning, but most of what I say, applies to all the algorithms here. And the last piece of terminology and taxonomy I want to do is to say, look, there are typically three types of learning people distinguish. At the top, there's supervised learning. So essentially, you learn with a teacher, as they say. So you learn by every single prediction you make, someone tells you it's right or wrong. The most standard way is classification in images. So you say it's a cat or not, and it tells you were right or wrong. And that's how you learn. It's nice, except that you need labeled data, as people say. And you need to know, you need to have lots of pictures where you know whether it's a cat or not. Let me jump to the right quickly. The other thing is unsupervised learning, where you have no explicit teacher. So unsupervised learning is a bit of a misnomer, because you need feedback to learn. You can't learn without feedback. It used to be not so important. It was mainly used for clustering. That changed dramatically over the last years because of something called self-supervised learning that I'll explain quite a bit in the sequel. And the last part, that's technically in the middle, if you get occasionally a signal if it's okay or not. And that's called reinforcement learning, because reinforce it by occasionally saying yes or no. While it might seem in the middle, basically supervised learning and unsupervised learning have very, very similar methods, whereas reinforcement learning is very different. I'll get to that setting. It's a very, very old learning theory, also used a lot in psychology and engineering, and has gotten a big revival with deep reinforcement learning, and it's now used a lot in games, robotics, etc. So these I'll get to, but just so you have once the terminology together. Now, one more thing that's useful to know is what are the capabilities of AI? Because often you don't use, you don't go into the algorithms itself, so you should know what can it actually do. And typically people distinguish around roughly 8 capabilities. Most people agree more or less on these. We've clustered it into 3 and say, interactive intelligence, which has to do with vision, language addition, analytic intelligence, the huge forecast and discovery, planning and search, And then motion, creative intelligence, so robotics and control, creation, etc. The interesting thing is, if you do a classical intelligence test, all it measures is analytic intelligence. That's what you typically measure when you try to see, is a human, the degree of intelligence of a human. You know, how good is he or she in recognizing patterns, in forecasting, etc. Diving. Now, as usual, as Moravec once said, what's easy for humans is hard for machines, and the other way around. We realize that interactive intelligence, vision with unstructured data, and motion and things are much more harder problems in learning. We just were, trained by a few million years of evolution. So we're very good at those. But they are actually the big problems. And most of the real dramatic breakthroughs over the last years were in interactive intelligence and motion creative intelligence, and that enabled AI to be deployed all over. Okay. So with that, we can try to go into to say, okay, what are some of the core methods that you will see within those? Some of them laid out here, where they're used and what you should know about them. So first of all, I told you before, artificial intelligence is about inductive learning. So deductive is deterministic. You do a rule, you program and deploy. Artificial intelligence is inductive. So you do a little learning algorithm, give it data, and then you train, test, deploy, retrain, etc. So it's inductive intelligence. Now, I'll explain it, so to say, first, take a very traditional algorithm and say, okay, how did you do it? And how do you do it? Actually, a very powerful algorithm, one of the most powerful that doesn't involve deep learning. And that's, starting with decision trees. Most of you might be familiar by decision trees, and you can try to learn a decision tree in order to make a prediction. This is a standard decision tree derived for, would you have survived the Titanic disaster? And it's funny, decision trees are used a lot in business, and no one ever thinks about how to set it up, but there are actually optimal ways to set it up. So you try to be as discriminative as possible in the first layers. So the most important thing you had to ask is, was it a male or female? Females essentially survived, had a 73% of survival. Males had a much worse fate. If you were a male, actually the next discriminative is how old were you? Below or above 10 years, essentially. If you were above 10 years, you almost certainly died. If you were below 10 years, interestingly, you thought, okay, they would have saved the kids. Well, that was not quite true. If you had more than 2 siblings, so you were more than 3, you'd still died, probably because your parents didn't know whom to save. But if you had few siblings and were a kid, then you had a very good chance of survival. It's obviously a very trivial tree, but it's something that you say, okay, it's also very rigid and so to say in itself, while it's widely used in decision taking, not so useful. But based on that, you can actually build with very simple methods a very powerful learning algorithm. It's called random forest. It's very simple. You go from a tree to a forest by actually doing lots of trees. You average over many trees, so-called ensemble. That's why I call it forest, and you call it random because these random trees are produced by omitting some nodes. So let's say you don't know age, you omit some data points. That's the method called bagging, and it's done randomly. That's why I call it random forest. And it might seem very simple. It's actually extremely powerful algorithms. It's very strong in many business applications. Almost the first thing you do, and is your baseline. And the nice thing is rather easy to interpret, right? The decision tree is very easy to interpret. Everyone understands a decision tree. And the same is still true for random forest. You can still say what are the most important criteria, what are the most discriminative criteria, in what order should you do it, etc., etc. So it's fast to implement, etc., etc. So there are some of these powerful things, and if you just have a standard business model. You try to predict the next best action for an insurance agent, or you try to do some marketing optimization or so. That can be quite powerful. However, things change quite dramatically when you went from structured data to unstructured data. And when you say unstructured data, most people think of language and pixels or vision. There are other unstructured audition and so on, but they are much easier. They're trivial, I mean, not trivial, but they're much easier when you apply Fourier analysis, and you can apply the same methods that you do for language and vision. And that to approach that, the big breakthrough was in 2012 by doing neural networks, and I say at least a few salient aspects of neural networks that everyone should understand. So I hope you have a basic understanding, because I've been rather fast, but I will be complete. So if you don't and listen very carefully, you should be able to follow. So here's a neural network. I take the standard setting. Neural networks, as you might know, are inspired by the human brain. In the 40s, they took apart cat brains and learned a lot about what the brain is like. And the neural network essentially has an input layer here at the top. I'll use a lot the example of pictures and the prediction of cats, because there's zillions of cat pictures on the internet. That's why they're so popular. So you have an input layer. Think of pixels. So think of a real abstract input layer. And pixels are turned into numbers by just having the gray shades and where they are. And the target is a cat, no cat. So you just have some kind of prediction, classification, sort of. And in between, you have nodes. In the brain, they're called neurons. And you have edges in the brain, they're called nerves and synapses. So you have connections. So that's essentially the basic structure. You have layers, you put them in nice layers, you connect everything via edges, and then they go through nodes. And then you have to answer two questions. How do you make a prediction, and how do you learn? And both are extremely easy methodologically in neural networks. That's why they are so easy to understand at that level. So how do you make a prediction? You just, so the input layers are numbers, and you multiply them by weights. The edges have weights. You can think of, in the nerve cells, they're actually widths. The nerves can be wide or small, and depending on that, the signal is larger or smaller. And so just think of weights that just get multiplied by weights, and then you sum them up. So you have a weighted sum. That's how you make a prediction. And you can think of, in every of these nodes, you make weighted sums, and then you send them forward, and you make other weighted sums, etc., etc. And at the end, you get something that's bigger than 0, then say it's a cat, or smaller than 0, that say it's not a cat. And you initialize these weights randomly, so you get complete nonsense. So the second thing you have to answer is, okay, you know how to make a prediction. How do you learn? And the learning idea is also very simple. It's a little bit, think of being in the mountains in fog. And you want to get to the valley. What do you actually do? And the valley, we use valleys because it's to minimize mistakes, so to say. So the best chance you have is to take the step in the deepest direction downwards. It's called steepest descent, or more technically gradient descent, and that's what you do. You adjust the weights a little bit, so your prediction would have gone a little bit. Say you made the wrong prediction or the right prediction, you made the wrong prediction, I said, no cat, you adjust the weights a little bit, so the chances of having a right prediction increases a little bit. And if you think about it, it's really very similar. It's a picture in weight space, so you continue to adjust these weights, and in the end, so what you learn is the weights, how fast you transmit the signals, so to say, how much you weigh them. And if you continue that, ideally you land in a valley. Now you might say, no, I can land in lots of intermediate things, but I'm not sure I get all the way to the valley. I can go into a little side valley. That's true in 3 dimensions. Fortunately, you have millions of dimensions. In millions of dimensions, you essentially don't get stuck. There's always a way out. So you're not easily stuck. It's very hard to prove anything about neural networks, but it works rather well with a few tricks that you find the minimum. And you repeat that zillions of times. And in the end, it actually learns to distinguish a cat. Obviously, there are some more tricks. The most important trick that is still missing, it's also true for brains. In brains, not every signal gets transmitted, but you need some activation. And the first thing you introduce is here, so to say, an activation, also called non-linearity to the output. So you only transmit the signal if it's bigger than 0. And if it's bigger than 0, you then can transmit it in lots of ways. I mean, you can do lots of things, but you have to essentially have some kind of barrier so that don't transmit all the signals. That's actually extremely critical. It's called breaking the linearity. So linearity, essentially, if you only have straight lines, so this line is not exactly straight, it has a kink. It's the most basic non-linearity you could possibly imagine. So everything is set to 0 and everything is unchanged. It's called ReLU, like rectifier, like in electricity when you do alternating current into direct current or the other way around. For those of you that are, technically minded, it's the simplest nonlinearity you can introduce. It costs you no computing time, and from something that can learn almost nothing. If you don't do that, you can prove that it can learn almost nothing. This network, you get to something that can learn almost everything. That's what I said. Going from linear to nonlinear is true. So that was the basics of neural networks. This is the basis for almost any frontier application involving large-scale unstructured data. It scales extremely well. So if you give it zillions of data, it becomes much more powerful. All the others flatten, all the other algorithms that we've known so far. It's not so easy to interpret, right? It's totally pointless to say what pixel was most important, right? It's just a nonsensical question even. And the whole thing that we did previously, we tried to do features, like we had gender was important, age was important, and so on. That kind of falls apart here. There's lots of work in how to interpret neural models, but even that has neural networks, apologies, that has evolved a lot over the last years, but is basically still extremely hard. So that's why people like these random forest plots. If you don't need a neural network, don't use it. Okay, you continue now from here. Now, for those of you who've never used that, I recommend something. Use the TensorFlow Playground. Just Google it. It's actually pointed up by Google, where you can build a neural network. You can build neurons, and it recognizes a two-dimensional pattern. 2 dimensions are wonderful because you can look at all the neurons, what patterns they recognize, and you can see very clearly what happens in the first layers, how they learn simple edges, how they learn more and more complex, complex aggregations. You essentially have to abstract more complex. They learn balls, they learn, all kinds of shapes. Ultimately, they learn noses and ears if you have vision, but obviously not in these 2 dimensions, and how to distinguish them. It's a very cute thing. So if you've never done it, play around with it. You can add layers, you can add nodes, you can do all kinds of stuff. And I think blue was when it's positive, and yellow, I think, when it was